Hello everyone, so in this video we are going to discuss about properties of LTI systems. So here LTI means linear time invariant system. So linear and time invariant. So we have already seen these two properties in detail in the previous video. So in this video we are going to discuss about the properties of linear time invariant system. So we know from our previous understanding that any continuous time or discrete time system can be represented in terms of their unit impulse response. So any continuous time or discrete time system can be represented in form of their unit impulse response, and in discrete time it is represented in terms of convolutional sum, and in case of a continuous time it is represented in form of convolution integral. And we can write the expression for the output as yn is equals to summation k is equals to minus infinity to infinity x of k h of n minus k, and it is equivalent to xn convolution with h of n, and this is for discrete time case. Similarly, for the continuous time case we can write yt is equals to integral minus infinity to infinity x of tau h of t minus tau d tau, and this is again equivalent to xt convolution with h of t. So the advantage of representing system help in determining the characteristics of the system by its impulse response. So when we write our output in terms of impulse response, we can characterize the system easily. So this will help in getting the characteristic of system, and we'll further see that how this can be done. So we'll start with our first property. So the first property is the commutative property. So commutative property states that if we have an input xn and the impulse response is given by h of n, and if they are convolving, then the order doesn't matter, like it is equivalent to h of n convolve with x of n, and equivalently it can be represented as k is equals to minus infinity to infinity h of k x of n minus k. And similarly for the case of continuous time, it will be xt convolve with h of t, and this will be equivalent to ht convolve with x of t, and this is again equivalent to minus infinity to infinity integral h of tau x of t minus tau d tau. So how can we prove this, like this commutative property holds? So there is a simple derivation of it. So we have to just replace a variable r which is equals to n minus k. So we'll take the condition of discrete time. So here let's replace this variable. So what we will get? We'll get xn convolve with hn. This will be equivalent to, now we'll use the definition of convolution, and this will be equal to summation k is equals to minus infinity to infinity x of k h of n minus k. Now we'll do the replacement of r over n minus k, and k will be written as n minus r from this equation. Suppose this is equation number 1. So this can be equivalently represented as r varying from minus infinity to infinity x of n minus r h of r, and if you closely see what it represents, it represent h of n convolve with x of n. So as you can see, it is equivalent to saying that here xn was input and hn was impulse response, and when we change the order, hn becomes the input and xn becomes the impulse response. So this property says that the order doesn't matter and they are equivalent. So next we'll move on to the next property, that is the distributive property. So the distributive property says that the convolution distributes over addition. So it distributes over addition. So how we can show it mathematically? So it can be shown as, for a discrete time signal xn, we can write xn convolve with h1n plus h2n, where h1n and h2n are the impulse response of the two systems, and this is equivalent to writing x of n convolve with h1n plus xn convolve with h2n. So these two expressions are equivalent, and similarly for the case of continuous time, we can write xt convolve with h1t plus h2t, that will be equivalent to xt convolve with h1t plus xt convolve with h2t, and again h1 and h2t are the impulse response of two continuous time systems. So what is the use of this property? We'll see explanation here. So by virtue of this property, a parallel combination of LTI system can be replaced by a single LTI system whose impulse response is just the sum of the individual unit impulse response. So let's understand the statement by a block diagram. So here suppose there are two systems represented with h1t and h2t, and suppose the input to this system is x of t, both of the system, and similarly the output of first system will be y1t and output of the second system will be y2t, and then we are adding these two to get our output yt. So mathematically how we can write this? So y1t will be written as xt convolved with h1t and y2t convolved with, it will be equivalent to xt convolved with h2t, and when we add these two, what will be the output? y1t plus y2t will be equivalent to xt convolved with h1t plus xt convolved with h2t, and by using the property we can write that xt convolved with h1t plus h2t. So your final output yt will be xt convolved with h1t plus h2t, and when we try to visualize this expression in terms of block diagram, we can say that it is basically a system represented with sum of the individual system, and xt will be the input to this system and the output will be yt. So a parallel combination which is represented by this block diagram can be replaced by a single LTI system whose impulse response is sum of individual unit impulse response in parallel combination. So using this property we can achieve that. So next we will discuss the third property, and the third property is represented by the associative property. This is the third property. And what it says, we'll directly go to the representation. So for discrete time, it will be equal to xn convolve with h1n convolve with h2n will be equal to xn convolve with h1n and convolve with h2n. And similarly for the case of continuous time, it will be xt convolve with h1t convolve with h2t will be equivalent to writing it as xt convolve with h1t convolve with h2t. So order of convolution doesn't matter. So the moral of the story is that order of convolution does not matter. So now we'll see this property in a better detail by some block diagram. So suppose we have a system represented with h1n and another system represented with impulse response h2n, and yn is your output, wn is your intermediate output, which is an input to the second system, and xn will be your input. So this can be represented equivalently using the property as h1n convolve with h2n, and the input to the system will be x of n and the output will be y of n. Now using the commutative property which was already discussed, we can change the order. So from h1n convolution h2n, we can write it as equivalently as h2n convolve with h1n, and the input to this will be xn and yn. So here we use the commutative property. Now, and this can be equivalently represented as, so now this will be changed to h2n, this will be h1n, and again x of n is the input and y of n will be the output. So when you compare these two block diagram, so this is your first, this is your second. So when you compare the first and second, you can clearly say that the order of convolution doesn't matter. So here is a note, like these properties strictly valid for linear systems. So suppose the system is non-linear, so this property does not hold. So we'll just give an example to understand it properly. Suppose we have a two memoryless system. So we have two memoryless system, and one is squaring. So one operation, first system is operation of squaring, and second system is multiplying. So second is multiply by a factor 2. So suppose we first square and then multiply it with by 2. So what will be the output? Output will be yn is equals to 2 into x square n. And suppose we first multiplied by 2 and then square, then what will be the output? Yn will be equal to 2 of xn whole square, which will be equal to 4 of xn square. So as you can see that these two are not equivalent. So these properties are strictly valid for a linear system. Now we will see some of the properties which we have already discussed in a crude manner. Now we will discuss it with terms of system, and we will see how they are related to the impulse response. So we will discuss about a LTI system with and without memory. So we will discuss LTI system with and without memory. So in the previous video I already explained that what is a memoryless system, what is a memoryless system. So memoryless system, just to reiterate, It is a system in which if the output at any time depends only on the value of input at that same time. So the output at any time depends only on the value of the input at that same time. And we have already seen the example, so I am not getting into the example. We will see this property with respect to the impulse response of a system, or basically LTI system. So suppose we have Yn, which is represented as a convolution of input and the impulse response. Now if we want our system to be memoryless, what will be the condition for Hn? So Hn must be 0 for all values of n which is not equal to 0, because we want the output at any time depends only on the value of input at that same time. So for any other value of n, the Hn should be 0. And how can we represent it within some different form? So we can write it as Hn is equals to k into delta n, where delta n represents your impulse response. And what will be the final expression when we replace it here? It will be Yn will be equal to k into xn, and k is basically your h of 0. And if h of n is not equal to 0 for n not equal to 0, the system is said to be having a memory, so it has memory. And any example we can give, so we can just write impulse response h of n, which is taking a value of 1 for suppose n equal to 0 and 1. So it is taking value for 1 other than value of n is equals to 0, that's why it is having some memory also. So it will be 0 otherwise. And similarly for the case of continuous time, we can write it as yt is equals to, so it is the case of continuous time, yt will be equal to some k of xt for ht is equals to k delta t. Again we are saying that ht must be equal to 0 for all t not equal to 0. So this is the LTI system with and without memory. Now we will see the stability of an LTI system. So next we are going to see the stability of LTI system in terms of its impulse response. So first we will discuss what is stability, though I have already explained in one of my previous video. So I will just give the definition. So a system is stable if every bounded input produces a bounded output. So every bounded input produces a bounded output. So let's see it with some expressions. So we have xn whose mod value is less than b, and b represents some bounded value, and this is for all value of n. Suppose this is equation 1. So we can write yn in terms of the convolution sum as k is equals to minus infinity to infinity h of k x of n minus k, and we are interested in the mod value of these. So from the property that magnitude of the sum of set of numbers is no larger than the sum of the magnitudes of the number, so we can write here as yn should be less than equal to k is equals to minus infinity to infinity, so mod of hk and mod of x of n minus k. And from this equation, equation number 1, we can say that x of n minus k mod is less than b, because we have already said that the input is bounded, and this is for all value of k and n. So now replace it into the equation number 2, what we'll get? We'll get yn as less than equal to b times summation k is equals to minus infinity to infinity mod of hk for all values of n. And what this implies, that summation for a system to be stable, summation k is equals to minus infinity to infinity mod of hk should be less than infinity. So this is the complete sufficient and necessary condition for the stability of an LTI system. And similarly, for the case of continuous time, we can write it as minus infinity to infinity mod of h tau d tau should be less than infinity. So this is the property of stability of a LTI system. So let's see a short example. Suppose a system is there that is pure time shift in either continuous time or discrete time, and suppose we have taken the time shift operation in case of a discrete time. So it is represented as n is equals to minus infinity to infinity mod of h of n is equals to minus infinity to infinity. So our signal is the shifted version. So suppose it is del of n minus n naught, and as we know that this value will be equal to 1, that is happening at the value of n is equals to n naught. So this is a stable system. But suppose the impulse response is a form of unit step, so it will be n is equals to minus infinity to infinity mod of u of n, and that is basically infinity. So this system will be unstable. So this is the property of stability of an LTI system in terms of impulse response, and these are the two sufficient and necessary condition for the case of discrete time and the continuous time system. Now we'll discuss about the invertibility of an LTI system. So we'll discuss about the invertibility of LTI system. So again, we'll give the definition of invertible system, and for detail you can refer to one of my previous video. So a system is invertible only if an inverse system exists that, when connected in series with original system, produces an output equal to the input to the first system. So a system is invertible only if an inverse system exists that, when connected in series with the original system, produces an output equal to the input. So it will produce an output which is equal to the input to the first system, which is equal to input to the first system. So to understand with it with some block diagram, we can write it as, suppose there is a system HT and other system is your HIT, that is inverse to your first system. So if xt will be input to the first system and yt will be the output to the second system, and that is the input to the next inverse system, then the output will get wt, which will be equal to your input. So it will be same as that of your input. So how this will be possible? So if these two system will be equal to, so the convolution of suppose h1t, that is the inverse, and your original signal will be equal to delta t, then only it is possible. So suppose these two is replaced with a single system whose impulse response is delta t, then if you will give you an input of xt, you will get the output as xt. So this signifies that h1t convolve with h2t will be equal to delta t, then we can say that the system is invertible. And similarly, for the case of discrete time, the convolution between the signal and its inverse system will be equal to del of n. So let's see a property, this property with help of an example. Suppose we have an impulse response Hn which is equals to u of n. So Yn can be represented as minus infinity to infinity x of k u of n minus k, and we all know that u of n minus k will be equal to 0 for n minus k less than 0, and it will be equal to 1 for n minus k greater than 0. So then Yn can be directly written as k is equals to minus infinity to infinity x of k, and you can see that this is the expression for the accumulator. Now in the previous video we have seen that the inverse to this system x accumulator will be Yn is equals to x of n minus of x of n minus 1, and we have take the inverse system response as del of n minus del of n minus 1. So when we convolve h of n with inverse impulse response, what we will get? We will get un, because Hn is we have taken as un, and when it will convolve with del of n minus del of n minus 1, we will get un convolve with del of n minus un convolve with del of n minus 1, which will be equal to un minus un minus 1, and that is your impulse, unit impulse signal. So as you can see that Hn, the convolution of Hn and H inverse n is equals to del n. This means that inverse to this system the inverse to this accumulator system is this expression Yn is equals to xn minus x of n minus 1. So these were some properties we have discussed about linear time invariant system, and we'll see and use further in solving problems in our upcoming videos.